Okay, in my previous video, I illustrated how to carry out simple linear regression using Stata 14. And so what I want to do in this video is to extend that discussion and talk about evaluation of model assumptions. Basically, with each statistical test, there are assumptions concerning your data. And when those assumptions are not met, then it can lead to an increase in type 1 or type 2 error rates. So what I wanted to do is to go over a few of the assumptions related to regression analysis and focusing mainly on simple linear regression, and look at some strategies for evaluating those assumptions using Stata. So for starters, what I've done is I've called up the previous data set where I'd run the regression analysis into the program. So under Data Editor, you can see I've got several variables here. I'm looking at the predictive relationship between performance goals and achievement. And I'm just going to quickly rerun the analysis because basically to evaluate the assumptions and carry out subsequent tests, you're going to actually have to run the regression analysis first. So what I'm going to do is I'm just going to ask for, I'm going to put achievement as my dependent variable and performance goal as my predictor. I'm going to indicate that it is continuous. If the variable is not continuous, then I would leave this unchecked. If it was a factor, then basically what would happen is that Stata will essentially create dummy variables for you, and that will be included in the analysis. So click on add to variable list, okay, and so that variable appears here, and then I'm just going to click on submit, and there's my regression results. So these are the least squares regression results. Now concerning the assumptions related to the model, you have several. One is independence of observations, and a second, and more specifically, independence of the residuals. Second, you have normality of the residuals, which are, when I use the term residuals, I'm talking about prediction errors. You also have homogeneity of residuals or prediction errors as well, and then you also have linearity between your predictor variable and your criterion variable. So what I'm going to do is start off by looking at the linearity assumption. So in other words, I'm going to test or evaluate the degree to which performance goals and achievement, which is achievements, again, my criterion or dependent variable, whether that relationship is linear. So one of the quickest ways of looking at this is using a scatter plot. So I can go to graphics, to a graph, and under create, I will, it just says scatter plot. So I'm going to put my criterion variable or dependent variable into the Y box, my predictor into the X box, click on submit, and so now you can see that I have a scatter plot. So this is just a plot of the coordinates, the XY coordinates for each case in my data set. It actually has data on both variables. So as you can see, there's a general trend, more of a negative trend in the data, which is really which is obviously going to be consistent with the coefficient, which is negative here. Basically, as scores on performance goals were increasing, scores on predicted scores on achievement are decreasing, and so forth. So we have a negative predictive relationship here. Now, if I want to ask for a fit line, which kind of helps me to better evaluate linearity, then what I can use is this little command line down here. So again, I've generated the basic syntax to get a scatter plot, and we can modify this just a shade and generate a fit line. So I'm going to type in scatter, achieve as my dependent variable, performance goal as my predictor variable, and then I'm going to type in L fit. So it's basically going to give me a straight line, which is going to be used to fit to the data. So now I'm going to type in achieve, performance goal, and then press enter. And so now you can see I have a line of best fit to the data. So, and it's a straight line. So As you can see, but overall the trend is negative. It looks like the line is actually being pulled probably by, this may be an outlier up here, so the line is a little bit flatter than what I would probably expect. Without that particular data point, it would actually look a little bit more, the slope would be a little bit greater. But nevertheless, you can see that the data generally seems to be following a linear trend. And now, let's say I want to see if there's another type of trend, like a quadratic trend, basically sort of a curvilinear relationship, or where there might be a bowl shape in the data. What I can do is still type in two-way, scatter, achieve, performance goal. In this case, instead of typing in L-fit, I'm going to type in Q-fit, and then my dependent variable name, and then my predictor variable name, and hit enter. And so you can see that the line is not quite straight. There's a little bit of a bend there. It's not much, and for the most part, the data is actually fitting. Overall, it seems like it's fitting a fairly linear trend. What I was really looking to see is, if the data, if you had sort of a bowl shape in terms of the relationship between X and Y. Something that might look more like, this, or, something more like this, or this even. So we don't have any of those kind of situations that appears in the data. So it looks like, in general, the data seems to be fitting more of a straight line. So at any rate, so that's a good way that we can look at the linearity assumption just visually, and trying to assess whether that assumption is met. Another assumption is that of normality of residuals and also homogeneity of residuals. And so what I mean by that is that the regression equation, you have to, in order to understand those kind of concepts, you have to understand something about what the regression equation is doing, or the prediction equation is doing. So what we're doing is we're trying to predict scores on the dependent variable, in this case achievement, as a function of the predictor variable. So we can generate predicted scores for each person in our data set by computing, or just taking the intercept, which is this right here. That's the intercept value. So it's 4.41 plus the product of the regression coefficient, which is negative 0.03, times the score on the predictor variable X, which is performance goals. So obviously we can kind of simplify this a bit and just say predicted values on Y is equal to 4.41 minus 0.03 times raw scores on X. So essentially it's like this. What we're doing, if we have our data, and I'm just going to give sort of a rough plotting of the data, but essentially the data is kind of following this type of trend. So these are the XY coordinates for each observation in the data set. And so and what we're doing is we're generating a prediction line. So the prediction line is essentially generated using this equation right here. And essentially, so these are essentially predicted scores on Y. So if you can imagine, we have the coordinate for X and the observed score on Y right here for a given person. Then we also have a coordinate for X and the predicted score on Y for a given person. So this is basically, reflecting the actual score on Y, and then this down here, this is on the line, this is reflecting the predicted score on Y. So I'm just going to use little Y hat right here. So basically, for every observation in our data set, there's an actual score on Y, and then there's also a predicted score on y. So the thing about it is that the difference between these two is, so if we just take y minus y hat, this is called prediction error, or so another term for it is a residual. So in effect, what we're looking at is that for every observation in our data set, there's a predicted score on y and an actual score on y. The difference is called a residual. So each case will have a certain amount of prediction error associated with it. If you happen to have an observation, like an actual score on y, that actually falls right on the prediction line, then the prediction error would be 0. You know, when it's off the line, like if your observed value on y is greater than the predicted score on y, let's say this is predicted, this is observed, then obviously in this case the prediction error would have to be positive. If you happen to have an observation that's falling below the line, then you would actually have a negative prediction error. So, you know, basically, the thing is that when it comes to our assumptions of normality and homogeneity of variances, basically there are assumptions related to the distribution of residual errors, or prediction errors. So let me kind of walk you over here. So kind of going back, I'm just going to redraw this. So there's my x, there's my y. So when it comes to, I'm going to draw the regression line here. So when it comes to talking about the distribution of prediction errors or residuals, we have assumptions related to normality of the residuals and homogeneity of the residuals. And kind of excuse me here, this is probably not the greatest drawing, but this is just to kind of highlight what we're talking about here. So the basic idea, let me get rid of that one there too. All right, so the basic idea of normality is that you could imagine these as a distribution of residuals at a given value on x. So there's, let's say this is a value of 1, a value of 2, a value of 3, 4, and so forth. So this distribution, one of the assumptions, the assumption of normality is that the residual errors exhibit a normal distribution around the predicted value, or each predicted value. So these are basically called conditional distributions of residuals. So the idea behind the normality assumption is that the distribution of residuals at each value of x would look like this. And pardon the way I'm drawing these things, it's kind of difficult to do it with this little pen tool. But basically all of the distributions of residual errors at each value of x would be normal in shape. The other assumption is that the distribution of residuals, that if I was to compute the variance for each of these, those distributions, or the variances of those distributions, would be equal. And that's what's called homogeneity of variances. So we have equality of variances of the residuals across levels of our predictor variable x. So, you know, in terms of evaluating these two assumptions, there are statistical tests as well as looking at these assumptions graphically. So probably if we want to look at these assumptions graphically, what we can do is to generate what is called a residual plot. So I'll just say it's a residuals plot. And I'm just going to truncate that a bit, so just say residuals plot. So essentially what this entails is, you know, when you're looking at these distributions, just keep in mind a couple of things. First of all, when we take all of the prediction errors, the sum of prediction errors across all cases is going to equal 0. So the sum of prediction errors is equal to 0, and obviously that also means that the mean of the prediction errors would equal 0 as well. So when it comes to the residual plot, basically what we do is we plot out our scores on X against the residuals. Okay, so we'll use our y-axis as the residuals, and so the mean of the residuals again is 0. So in a nutshell, what we're looking for in terms of a distribution of the residual plots for each value on X we're looking for the residual plots or the residuals to exhibit a random pattern of distribution. So in other words, we want them to not exhibit any kind of systematic, any kind of shape or anything like that, any kind of shape that departs from what you would expect if the distribution were random. So in other words, it's sort of we're kind of looking for kind of a box, if you will, in terms of the residuals. Oops. Again, it's a little tricky to use this little pen tool here. Let's see. There we go. So the basic idea is that what we're looking for with the residual plot, this is probably most handy for assessing homogeneity of variances, as well as assessing, you can use it to assess linearity as well as looking for potential outliers. So what we're looking for is, like I said, in general, a sort of a random display of points. Keep in mind too that essentially you can't really visually see the distributions, the normal distributions, but the basic idea behind normality too would be that these are normally distributed. Basically, it's just taking what you see up here and translating it into this type of plot right here. So at any rate, so in terms of evaluating homogeneity of variances with this type of plot, again, you're looking for sort of a random display of points. What you do not want to see is a situation that might look like this. So let's say I've got X and Y. Here's my mean of the residuals here. And let's say I had a plot of points that look like this. What you'll notice, hopefully, is that as scores are increasing on X, what you'll see is that the spread of the residuals is increasing as well. In other words, what we're observing is that the variation or the variance of the residuals is increasing. So there's a pattern there in terms of that we don't want to occur. We could also see a reversal of that. So if we observe something like a cyclical pattern in terms of the residuals, that would be evidence that we have a violation of our assumption. And what that basically translates into is, if we have our regression line. Let's say I've got my little regression line right here, and let's say I've got the distribution of prediction errors, or actually looking at the actual Y in relation to the regression line. You can see that in terms of the actual Y's relative to the regression line, that the distributions are increasing. So again, you've got very small prediction errors here. You've got a slight increase in prediction errors here, increasing prediction errors here, and so forth. And what that basically means is that the model is not functioning the same way across levels of your predictor variable x. So that would signify, again, that you have a violation of homogeneity of variances. And you can visually get a visual idea of that just by looking at the residual plot. So let's kind of take a look at a few of these things. So we'll start off, we'll look at requesting a residual plot. So the way that we can do this using syntax is to type in RVF plot, and then we type in recast, and in the, excuse me here, let me type this in, recast, and then scatter, and then click on OK. And so now we have a residual plot. So you can see that we have the unstandardized residuals. Here's our mean residuals, which again is just nothing more than the sum of the residuals. And so now you can see that, by and large, in terms of the plot, most of the area you can see that sort of random display of prediction errors. You do actually see in this particular case, there's sort of a case out here that is a little questionable. It might suggest that we might have an outlying case in that situation. So, but for the most part, it looks fairly like that box I was telling you about. So another way of sort of looking at this is, let's say if we wanted to further evaluate outliers and so forth, what we can do is we can generate the actual residuals and then plot those residuals against the predictor variable values. But essentially, I can generate the same residual plot just by first generating the predicted values. The residuals. I can just type in predict, and I'm just going to type in residual, and then I'm going to type in RESID. And so essentially with that command, the predict is basically saying generate the residuals, and the thing is that this term right here, this is basically the name of a variable that's going to be added to the data set. And so you can see that's actually been added right here. So this could be anything. This could be, I could have called this R, or I could have called this shoe. I could have called this anything, and that name would appear in the data set. This is the actual part of the command that tells Stata to generate the residuals. So the thing is that we can also generate standardized residuals with the use of the following command. So we can type in predict, and I'll just call it stand, and that, again, that's just the name. I'll type in stand R. That will be just the name of the variable that's going to be created and added to the data set. And then the command for this will actually be R standard. And so when I press enter, then now you can see that the standardized residuals have been added. So the nice thing about the standardized residuals is that it's also very handy in terms of assessing, looking for possible outliers in the data. So at any rate, if I want to plot out these residuals against the predictor variables, then I can just easily, again, type in two-way, scatter, achieve. In this case, my dependent variable is the residual. So I'm going to type in actually the name of my standardized residual, which is, this is the variable that has been created to my data set. So I'll just type in stand R, and then I'll just type in performance goals, and then hit enter. And so there's my plot of the standardized residuals. So again, it looks like there's a case out here that's a pretty possible outlying case, bivariate outlier in our distribution. So, one way that you can assess for possible outliers is looking for cases that fall, between that fall outside of the range of -2 and +2 standard deviation units or z-score units. So you can see that here you've got the +2 and the -2. So you've got a couple of borderline cases here and here. This is probably the most clear outlying case that we see right here. But nevertheless, the overall pattern, aside from that, is a fair amount of homogeneity in terms of the residuals. So there you go. So and quickly, let me just kind of show you. If you go to the data editor, just to kind of show you those new variables that have been added. Here are the unstandardized residuals, and here are the standardized residuals. So if I want to test, there's also statistical tests of homogeneity of variances, and so in this particular case, we can just type in E-stat IM test, and this gives one test of homoskedasticity versus heteroskedasticity. The other one is E-stat HET test. And this is yet another test. So essentially, the p-values that are printed out right here are testing for homoskedasticity versus heteroskedasticity. So in general, what you're looking for are p-values that are larger as opposed to smaller. So these are two different types of tests of homogeneity of variances. So if the p-value is less than, or is low and less than some pre-specified alpha level like 0.05, then that would be evidence in favor of heteroskedasticity, which means then that you would not be meeting your distributional assumptions as it pertains to the residuals. If the p-value is actually greater than 0, then that would be consistent with homoskedasticity. And what that would basically mean is that you're more likely to be meeting the assumption of the statistical test. So here you can see we have a p-value that's equal to 0.58, and another test, the Bruce-Pagan and Cook-Weisberg test, the p-value is 0.4329. So in both cases, the p-values are greater than, and I'm going to use alpha at 0.05 as the threshold. Then in this case, it appears that the data are exhibiting homoskedasticity, which is, again, consistent with the assumption of linear regression. So, based on a residual plot and looking at these two tests right here, it would appear that we have reasonable evidence of homoskedasticity as opposed to heteroskedasticity. Another assumption is normality of the residuals, which I had mentioned earlier. And in order to evaluate that assumption, we have both a graphical approach as well as a test approach that we can use. We can go to graphics and a histogram. And what I'm going to do is I'm just going to move my residuals up to this box right here. We're going to assume that the data are continuous. And also, if I go to density plots, I'm going to add a normal overlay, a normal distribution overlay. Click on Submit, and so now you can see that I have the histogram of the residuals and a normal curve overlay. And it's not perfect in terms of exhibiting normality, but there's fair evidence of normality of the residuals. So that's a visual indication. And then we also have, we can use the Shapiro-Wilk test. So I'm going to just type in S-Wilk, and then the name of the variable that I want to test for normality. In this case, I'm using residual again. So I'll just type in residual, and then press enter. And so now we have a statistical test of normality of the residuals. So again, just like these tests up here concerning homogeneity of variances, we don't want this to indicate statistical significance, because if it does, that would suggest then that our data are departing significantly from what would be expected with a normal distribution. And so in this case, we have a p-value that's 0.4385, which is greater than say 0.05, and that would suggest then that our residuals are normally distributed. So at any rate, like I said, when we're talking about heterogeneity of, the homogeneity of variances and the normality assumption, we're talking about these in reference to the residuals, and so that's essentially what we've tested out in both of these cases. So that's the last assumption of independence of observations and essentially independent residuals. The basic idea behind that is that again the residuals are exhibiting a normal, a random display of points. So kind of going back and asking for, we'll just ask for again the our previous residual plot. So I'm just going to again type in RVF plot, recast, scatter. And so again, we're just looking to see if there are any non-random displays of residuals in the data.